Microswarm robots are small, autonomous machines that work collaboratively to perform tasks beyond the capabilities of individual robots. Inspired by the collective behavior of social insects like ants and bees, these robots rely on decentralized control and local interactions to execute complex operations. Their potential applications span across industries, including medicine, environmental monitoring, disaster response, agriculture, and construction, making them a breakthrough in automation and robotics. Microswarm robots are typically constructed using microfabrication techniques, allowing for production at millimeter or even micrometer scales. They are built using materials like silicon, polymers, and metals, depending on the intended application. Actuation methods vary, including magnetic fields, piezoelectric forces, and electrostatic mechanisms. These robots operate similarly to ants, following decentralized control principles. Each robot receives simple task commands and relies on local sensors to communicate with its neighbors. Communication is typically achieved through infrared signals, radio waves, or magnetic fields, allowing them to react to changes in the environment dynamically. By following programmed rules and observing their surroundings, swarm robots can coordinate movements and accomplish complex tasks collectively. The concept of swarm robotics was first introduced by G. Bainey and J. Wong in 1989, describing systems of simple agents exhibiting self-organizing behaviors. Since then, researchers worldwide have developed micro-swarm robots to study and utilize these behaviors in real-world applications. If you're new to my channel, please check out my videos and consider subscribing for more content like this. Thank you for your likes, shares, and subscriptions. Kilobot. Developed by Harvard University, Kilobot is a low-cost robot designed for swarm robotics research. Each unit costs approximately $14, making large-scale experimentation feasible. In 2014, a swarm of 1,024 kilobots demonstrated their ability to self-assemble into complex shapes. Colias is a micro-robot created by the University of Lincoln, inspired by the swarming behavior of honeybees. Measuring less than 2 inches in diameter, it serves as a low-cost platform for studying collective behaviors. Hero 2.0, an ultra-low-cost 3D robotics platform costing just $18 per unit. It includes expandability via eHat add-ons, allowing for customization and enhancement of capabilities. Significant progress in microswarm robotics has been made worldwide, improving their efficiency and expanding their applications. Researchers at Hanyang University in Seoul have developed tiny magnetic robots capable of collaborative tasks such as moving and lifting objects much larger than themselves. These microrobots, powered by rotating magnetic fields, demonstrate potential applications in minimally invasive medical treatments and environmental monitoring. Harvard's Wyss Institute has been pioneering in bio-inspired microswarm robots, including soft-bodied robots that mimic natural organisms for better adaptability in dynamic environments. Researchers at ETH Zurich have designed microrobots that can swim through fluid environments, enabling future applications in targeted drug delivery and non-invasive medical procedures. Researchers at the Indian Statistical Institute have developed swarm robots for surveillance and security, showcasing applications in intrusion detection. Additionally, they have focused on multi-robot systems for cooperative transport, search and rescue missions, and industrial automation. Indian researchers are also exploring bio-inspired swarm robotics for digital agriculture, enhancing precision farming techniques. Teams from major institutions of China have created micro-swarm robots capable of forming dynamic structures, enhancing their use in industrial and rescue applications. In the medical field, micro-swarm robots can navigate through the human body to deliver medication precisely to affected areas, minimizing side effects. Similarly, their small size enables them to assist in procedures requiring precision, reducing the need for large incisions with a swarm of 50 to 200 robots. In environmental monitoring, micro-swarm robots can be deployed in oceans or lakes to detect contaminants and monitor water quality. Around 500 to 1,500 robots may be used for effective monitoring of large water bodies. Similarly, scientists use them to observe and collect data on animal behavior in difficult to access areas, with 50 to 200 robots needed for effective coverage. In search and rescue operations, micro-swarm robots can navigate through debris in earthquake or collapsed building scenarios to locate survivors and relay critical information to rescue teams. A swarm of 1,000 or more is often required for large-scale search operations. Similarly, they can enter hazardous environments like nuclear disaster sites or chemical spills to assess damage and gather data, with 100 to 500 robots typically deployed. In agriculture, micro-swarm robots can monitor soil conditions, plant health, and irrigation levels, optimizing farming efficiency. Swarms of 200 to 1,000 robots may be used depending on the field size. Similarly, tiny robots can autonomously detect and eliminate harmful pests, reducing the need for pesticides for effective pest control in large agricultural fields. In construction, micro-swarm robots can collaborate to build temporary structures in hazardous or remote environments. Similarly, they can inspect and repair bridges, buildings, and pipelines with minimal human intervention, with 100 to 500 robots typically deployed for routine maintenance. As research progresses, the future of micro-swarm robotics looks promising, with continuous advancements in AI, machine learning, and miniaturization. Thank you for watching this video. I'll catch up with you in another exciting video soon. Until then, goodbye and take care.